The following question reads that T is a saturated alcohol. So that's the first thing, saturated word, and it's an alcohol. Alcohol means that there is going to be an OH group in this. Saturated means it's not. What saturated means is that it's not. There's not going to be any double bonds, no carbon double bond carbons, no alkene functional group in this molecule. The question then reads that it was analyzed by mass spectroscopy and NMR spectroscopy. So both mass spectrum is used, and NMR spectroscopy, that is also being used. And in the mass spectrum, the molecular ion peak M was at mass to charge value of 74. So this molecular ion peak, which is coming out, this mass M over E, which has a value of 74, means that the MR of the molecule is going to be 74. So the entire molecule is going to have a mass of 74. This is the molecular ion peak. And the ratio of the heights of the M and M+1 peaks was 20.4 ratio 0.9. So the M and M+1 peaks and the ratio is also given. Using this ratio, you can figure out the number of carbon atoms can be calculated using this ratio. If you have the M and M+1 ratio, because the M+1 height is because of the carbon-13 isotope. So if the ratio is given, you can figure out the number of carbon atoms. Now part A of the question states, part 1, use the ratio of the heights of the M and M+1 peaks to calculate the number of carbon atoms in a molecule of T. So we're going to use the formula for number of carbon atoms. The M and M+1 ratio, their percentage abundance is given, their ratio is given. So I've written down the formula for the number of carbon atoms, which is 100 over 1.1 into M+1 height divided by M. The M+1 height is given over here. It's given as 0.9. So this would be 0.9 divided by the height of M, which is relative height, which is 20.4. So calculating this value and multiplying 100 into 0.9 divided by 1.1 into 20.4, the answer that I'm going to get is, on my calculator, it's coming out to be equal to approximately 4. So we're going to round that value off. It's going to be 4 carbon atoms. So that's the number of carbon atoms that are in this molecule using the M+1 and M heights, their ratio. We found 4 carbons. Moving to the next part of the question, which is that what is the molecular formula of T now? So what we already know is that T is a saturated alcohol. It was mentioned in the first line of the question. It's a saturated alcohol, so that means it has 4 carbon atoms. So I'm going to draw the many different possible alcohols, saturated alcohols. One could be that I can have 4 carbon atoms in a line, and it's a saturated alcohol. That means there's going to be an OH group, and the rest of the atoms are going to be hydrogen. So they would be saturated, means that all the bonds are going to be single bonds. There's not going to be any double bond. It's not going to have the alkene functional group. So these are all my hydrogens. So this could be one possible structure. I can count the number of carbon atoms. There are 4 carbon atoms. So that's C4. Let's write it over here. There are 4 carbon atoms. So this is C4. Hydrogen is, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are 10 hydrogens, and there's one oxygen. Another thing that I would like to mention is that it wasn't only this saturated alcohol that was possible. This is 4 carbon atoms, and it was a saturated alcohol, but there could be many different isomers that would have the same exact molecular formula. So it could be that the OH group could be on the second carbon atom, or you could have the carbon chains. The 4 carbons would not be arranged in a chain, but they would be branched. So that's 1, 2, 3 carbons, and a central carbon, middle carbon branch emitting from it, and the OH is at the end, very end. Or it could be another molecule where the 4 carbons are arranged in this manner in a branched fashion, and the OH group is in the middle carbon atom. So the possible structures of C4H10O are these 4. So you have these 4 isomers that are saturated alcohols, and that have the same molecular formula. Now remember, when you're trying to do the NMR question, make sure you come up with as many isomers as possible, as many examples as possible, because then moving towards NMR would become a lot easier. Understanding the NMR would become a lot easier. So our molecular formula is this one, and our options are that the molecule could be either one of these four isomers. Now I'm going to move to the next part of the question, which is part B. And there you have this NMR diagram drawn. In this part, the question reads that the NMR spectrum of T given below shows four absorptions. The absorptions at 1.8 ppm is a multiplet, and that at 2.5 ppm is a singlet. So the first thing is, if you look at the NMR spectrum, and these are your chemical shift values, you have a total of four different environments, four different proton environments, which means that hydrogen is going to have four different environments. So let's go back to our molecules that we drew, and we're going to figure out how many different proton environments are there in these four isomers, because the molecule, a saturated alcohol with the formula C4H10O, is going to be one of these four molecules. Now, if we focus on this first molecule over here, a saturated alcohol, you would notice that the hydrogen environments, if you look carefully, this CH3, this CH3, and this CH3, the hydrogens in this over here and the hydrogens over here, they are exactly in the same chemical environment. They're all bonded to the same carbon atom, which is bonded to OH. This CH3 is also bonded to the same carbon atom, which is bonded to OH. And the same applies to this. These hydrogens, they are bonded to the same carbon atom, which is bonded to OH. So they have exactly the same environment. So I'm going to circle that. So these hydrogens, these protons, they have exactly the same chemical environment. So they're going to resonate at exactly one frequency. And the other hydrogen, which is this one, it has a different chemical environment. So in this molecule, you'll have two absorptions. Two radio frequencies would be absorbed. These hydrogens would resonate at one frequency. This OH would resonate. This hydrogen would resonate at a different frequency. It's going to have a different chemical environment. It's going to have different shielding. So this cannot be the option, because the NMR spectrum that is given over here has four different chemical environments. There are four different hydrogen environments. So the first option, the first isomer that we drew, we can reject that isomer. Moving to the next isomer that molecule that I've drawn over here. Now this other molecule over here, let's figure out how many different hydrogen environments there are. If you look at these hydrogens over here at the end, the CH3 groups, two methyl groups, they have exactly the same environment. These protons have exactly the same environment because they're both bonded to the same carbon atom. So they're going to have exactly the same chemical environment. So these CH3 hydrogens, they have one chemical environment. They're going to resonate at one frequency. This hydrogen has a different chemical environment because it's bonded, its environment, its surrounding atoms are different. These two hydrogens, they have a similar chemical environment but different from the others, because this CH2 is bonded to an oxygen, so its environment, its neighborhood is different, slightly different shielding, so different frequency would be absorbed. And then you finally have a hydrogen, an OH hydrogen, a proton that would resonate at a different frequency. So this molecule over here has four environments, four different chemical, four environments of protons. So this could be a very suitable candidate for this particular NMR, because it also has four different chemical environments, four different protons in four different chemical environments resonating at different frequencies. So let's first look at the other two isomers as well. But this molecule over here looks a very good candidate, and we're going to try and match this with the NMR spectrum. But let's focus on this molecule now. Let's look at the number of hydrogen environments in this molecule. You would notice that these three hydrogens have the same chemical environment, so they're going to resonate at one frequency. These two hydrogens have a slightly different chemical environment. These two hydrogens have a slightly different chemical environment as well, and these two hydrogens also have a slightly different chemical environment, and this hydrogen over here has a different chemical environment. So the number of frequencies that would be absorbed would be, there would be 1, 2, 3, 4, and 5 different frequencies that would be absorbed. So there would be 5 different chemical environments. Remember one thing, that you should treat CH2 and this CH2 as different environments, because this CH2 is bonded to CH3, this CH2 is bonded to CH2s on both sides. So although they look pretty much the same, their environments are very similar, but they're not exactly similar. This CH2 has different things bonded, slightly different things bonded. This CH2 over here has slightly different neighborhood. So although they look very much the same, but there is a very, very slight difference, and you're going to treat the two differently, because this is resonating at a different frequency, this will resonate at a different frequency. This CH2 obviously is a lot different. The shielding is going to be different because it's bonded to an oxygen, so the environment of the hydrogen protons would be different. But you wouldn't be picking this molecule because it has a total of 5 different chemical environments. Let's look at this fourth isomer that we have drawn. You would notice that, let's see how many hydrogen environments there are. So these 3 hydrogens, they have, protons have similar environment. These 2 hydrogens have a similar environment. This hydrogen has a different environment compared to the others. This OH has a different environment. And this CH3 these protons have a different environment. Remember, this CH3 and this CH3, they're not exactly the same. This CH3 is bonded to CH2, whereas this CH3 is bonded to CHOH. So the environment surrounding these hydrogens is slightly different compared to the CH3 over here. So they're going to resonate at different frequencies. This would have a different frequency, this would have a different frequency. In total, you're going to have 1, 2, 3, 4, and 5 frequencies that would be absorbed, and 5 different chemical environments are present. Now, this, since we drew all the isomers, now it has become very easy for us to figure out the NMR spectrum and to figure out the molecule. And we have actually singled out the isomer because this isomer over here had 4 chemical environments. This was the only one that had 4 chemical environments. This had 2 environments, this had 5 environments, this also had 5 environments. So this is going to be your answer. So I'm going to take this molecule and now study this closely and try and match it with the NMR spectrum that's drawn at the bottom. So let's, if I've drawn this molecule over here, and I'm going to try and match it with the NMR spectrum that's drawn over here. 4 different environments, and you also have 4 different environments over here. So I'm going to first analyze these 2 CH3s, the 6 hydrogens that are over here in the same environment. If you look at these hydrogens, the first thing is they are very large in quantity. They are a lot in number, so that it's going to be a strong absorption. So I'm suspecting that this peak over here is going to be your peak for these hydrogens. And the way I can confirm it is by using the N+1 rule. If you look at this molecule, the neighboring carbon atom, the hydrogens are bonded to these carbon atoms. The neighboring carbon atom has 1 hydrogen. If it has 1 hydrogen, the peak is going to be a doublet, and which is true that this peak over here is a doublet peak. So this pretty much confirms it. Let's now move to this other hydrogen. It has a different environment because it's bonded to a carbon atom, and there's only 1 hydrogen bonded to this carbon atom. So it's going to have an absorption, but it's going to be a weak absorption because there's only 1 hydrogen. Plus, the peak is going to be a multiplet, because if you look at this hydrogen, the neighboring carbon atoms have a lot of hydrogens. If you look at this hydrogen over here, the neighboring hydrogens, this one is the neighboring carbon atom, and these are the neighboring hydrogens. So it's surrounded by hydrogen protons on the right side, at the bottom, on the left side. So the interference is going to be very, very high, and a lot of splitting would occur. So according to the N+1 rule, this hydrogen would have a multiplet. There would be a lot of interference by the neighboring hydrogens. So it's so this pretty much matches our information so far with our information. Then let's move to this OH hydrogen proton. Remember, OH does not split. There is no splitting. There's very little interference by the neighboring hydrogens for this proton because of the shielding by the electrons and lone pairs on oxygen. This hydrogen is very shielded so from the neighboring hydrogen, so there would be no splitting, and it would be a singlet peak. So this singlet peak over here would be this OH peak. So let's match that. And finally, the fourth chemical environment is of these two hydrogens. These two hydrogens, the absorption is not going to be very strong. And the neighboring carbon atom, there's only one neighboring carbon atom, one hydrogen. So according to the N+1 rule, these two hydrogens would have a doublet peak. So it's going to be this peak at the bottom, at the end. This would be a doublet peak for these CH2 hydrogens. Their protons are going to resonate at this particular frequency. And the last thing I'm going to do is I've actually figured out the molecule over here. But just to confirm, what I'm going to do is I'm going to look at the chemical shifts. This is at one chemical shift. I'm going to open the data booklet. Remember, at one chemical shift, my protons were these protons. They were protons on a carbon chain or alkyl chain next to an alkyl chain as well. So these protons are the ones next to alkyl chains or on alkyl chains. And they're resonating at one chemical shift parts per million 1. So let's open the data booklet and let's confirm that. So if you look over here, the alkane chain, the carbon chain, protons, they resonate around 0.9 to 1.7. So that is correct. The data is again matching the chemical shift that's given in the data booklet. This other one is at around 1.7. This is again also a proton that is on a carbon chain. So it's the same one. So from 1 to 1.7, this is the alkane, the protons on an alkyl or alkane chain. So that is correct. Then let's move to this peak, the singlet peak. This I assumed that it was an OH peak from an alcohol. Let's open the data booklet. It's resonating at around 2.5 chemical shift. So let's open the data booklet. Now in the data booklet over here, you would notice this normal alcohol OH proton, and our proton was resonating at 2.5. So it is within that range. So that also fits the chemical shift that's given in the data booklet. And let's finally look at these protons over here. These were these protons over here, the CH2 next to a single O, and this was resonating around 3.5. So let's open the data booklet. It's CH2 next to a single O. So over here you would notice this CH3 or CH2 next to single O. So it is again within that range. So the chemical shift values in the data booklet also match our molecule that we have drawn, figured out. So our in the next part, we were basically asked to draw or deduce the structure of T. We had to draw the structure of T over here. I have already drawn this structure of T over here. This is my final molecule that I've figured out. Moving to the next part. The next part is we need to describe and explain which type of proton is responsible for each of the absorptions. What I just need to do now is I've already done all my working. I just need to, you have protons over here. I just need to give the information that we are talking about these protons. The chemical shift over here, there's a chemical shift over here, and there's a chemical shift over here. So I'm going to quote these values and I'm going to describe which protons we are talking about. So here I've listed all the chemical environments. 0.9, there was a peak at 0.9, and I've underlined, I've drawn the molecule, I've underlined the protons that were responsible. It's these one. At 1.7, it was the CH proton, it was a multiplet. At 2.5 parts per million, it was OH, and at 3.5, it was again a doublet, a CH2. This CH2 was responsible for that. Now moving to the next part. The next part is that the absorption at 1.8 parts per million is a multiplet, and that at 2.5 is a singlet state. Explain the splitting patterns of the other absorptions at 0.9 and 3.4. Now going back to our diagram, 0.9 was a doublet. Reason was it was a doublet is because these hydrogens had one hydrogen as in its neighborhood. Hence, there was interference because of this hydrogen. These protons, their absorption frequency or resonant frequency split into two. And he was also talking about this peak. This peak was the CH2 peak. This also had one hydrogen as its neighbor, so it was also a doublet peak. So this is what I'm going to refer to in the answer. So here I've written this down. Neighboring carbon atom has one hydrogen in both cases. Hence, according to the N+1 rule, there would be interference and the peaks would split. A doublet peak would be formed. So that's the explanation. Now, the last part of the question is that describe and explain how the NMR spectrum T dissolved in D2O would differ from the one shown. Now, remember, D2O is deuterium. Deuterium is basically hydrogen, but it's an isotope of hydrogen having two nucleons. Now, when an atom has two nucleons, it's not going to resonate. It's not going to have an overall spin. So no resonance would be shown by this isotope. So this D is not going to resonate. Now, adding D, what D would do is that all the other hydrogens are very stable, the ones that are bonded to carbon. It's the OH hydrogen that would get displaced. It would get displaced, and eventually this OH hydrogen is going to be substituted by a deuterium atom or deuterium proton, which is not going to resonate, because alcohols, this OH would be constantly dissociating, producing H+1 ions, and it would be constantly combining back again. So there are chances, because the water contains D+1 ions, the other isotope of hydrogen. So there would be a lot of very high chances with that when the dissociation or when the H+1 combines with the O back again to form the alcohol back again, you might get deuterium replaced as the hydrogen in the alcohol. If it gets replaced, if D is replacing the H in the alcohol, then this would stop resonating and there would be no OH peak. So your peak at 2.5 parts per million, the OH peak is eventually going to disappear, because this hydrogen would be substituted by the other isotope, which is not going to show any resonance, because it doesn't have an overall spin. The spins are going to be paired. There are two nucleons. So this peak, this OH peak, is going to disappear.